Alright, in the last video we talked about the general theory for ionic solutions. We talked about the effects of ion-ion interactions, the presence of screening layers or counter-ion atmospheres, if you like, around everything in ionic solution and some of the consequences of that. Now we're going to talk about the consequences of the ion pairing itself, or the statistical ion pairing itself, specifically on the activity coefficients, and then also what those activity coefficients mean for the equilibrium of chemical species, chemical reactions, dissolving reactions, acid-base reactions, and the like in solution. Here's the general formula. I won't derive it because it's long and complicated and not very illuminating. And it's in a form that's not very useful right now because it's complicated. And I haven't even defined clearly enough anyway what this kappa is. We saw it above, right? That kappa is related to the Debye length by 1 over kappa. So you can see that the Debye length appears right away in this formula and is very closely related to the activity coefficient. But we have to fill all that stuff in. There's a bunch of constants inside there. We'll do that down below. In the meantime, let's talk about what this quantity that we're solving for here is. It's an activity coefficient. It's gamma, but it's called gamma plus minus. Let's suppose that we have some sodium chloride in solution. Then what we'd actually, the chemical species in solution, would be sodium plus ions and chloride minus ions. And you'd expect, from the way we normally write things, we normally write that the activity for, say, sodium plus would be an activity coefficient for sodium plus times the concentration of sodium plus divided by some standard state concentration. And so you'd expect there to be an activity coefficient for every different chemical species in solution. There'd be an activity coefficient for sodium ions, there'd be an activity coefficient for chloride ions, and so on. And this doesn't look like that. It's not labeled, sodium or magnesium or chloride or sulfate or something like that. It's labeled with this generic plus minus on there. And the reason for that is that it's not possible to actually measure, or calculate for that matter, the activity coefficients for individual ionic species. They're inseparable in solution. Whenever you get one, you get the other, so you can't separate them out and measure them individually. So to solve that problem, we define this mean activity coefficient. So that's what I say up here. These are mean activity coefficients. They're the average, in some sense, activity coefficient between all the chemical species that are in solution. And we'll see how to use them below. So let's suppose we're calculating, for example, the delta G for a chemical reaction for this chemical reaction. So we're dissolving some salt in water. That's our chemical reaction. We write down the delta G expression as usual. That involves, in this case, the activities for both of the products divided by the activity for the reactant. In this case, the reactant is a solid. So that activity is 1. And the activity for the two ions is an activity coefficient times the concentration. And I'm going to assume 1 molar standard state, so I'm not going to put the standard state underneath there. I'm going to assume it's a 1. And the same thing for the chloride. And so here we have that down here, and that would use these two activity coefficients for the individual ions. And then if we plug that into Q here, this is Q, remember, we'd get this. Here's Q. And you can see that what happens is that the activity coefficients come out and get bunched together. And when you actually calculate things, we could replace that product of two different activity coefficients by a single activity coefficient to the same power, right? This is 1 power, this is another power, a total of 2 powers altogether, and that's why we have a 2 up there. We've got 2 factors. We still need 2 factors when we're defining our mean activity coefficient here, so we put a square there. And we define that mean activity coefficient to be that this square is the same thing as the product of the two different activity coefficients. You can always do that. That means that this gamma plus minus is the geometric mean two different activity coefficients. Geometric mean means multiply everything together and then take the appropriate root instead of dividing by the appropriate number. So for example, if there were three chemical species in solution, the appropriate geometric mean, since there's now 3 powers, would be gamma A, gamma B, gamma C to the 1/3 power. And likewise, if there were 4, it'd be gamma A, gamma B, gamma C, gamma D to the 1/4 power, and so on. That's the geometric mean. So what that means is that there's only one activity coefficient for a given ionic solution. There's not a whole bunch of different ones. We're only calculating one gamma plus minus for the whole solution, no matter how many ions there are. And second, that this gamma plus minus is defined so that we still get the right answer. It doesn't matter that we don't know the individual ones. We can get the answer we want out, even so. And so, here's an example. With power 3 involved, so we're dissolving now magnesium chloride into solution. A lot of dissolving reactions in these cases because they produce ionic solutions, of course, and a dissolving of ionic salts anyway. And so in this case, we're going to write delta G again. We're looking for this Q. Q is this combination of products over reactants for activities. There's a square now because 2 chloride ions are produced every time a magnesium chloride dissolves. And so it's A for magnesium 2 plus, A for chloride squared, divided by A for the solid, which is going to be taken to be a 1 down here. We put our mean activity coefficient in there instead of individual activity coefficients. Now, because this is squared over here, that ends up being activity coefficient plus minus cubed times the concentrations, the normal molar concentrations. And here, that mean activity coefficient is in fact the geometric mean, just like I was talking about above. All right, so with that, we now want to make this formula more useful, easier to calculate. And so to do that, I've pulled out all of the extra constants, so all these extra fundamental constants and all the constants that are buried inside of that kappa. I've pulled them all out and put numbers into them and assigned units, appropriate units to them, and so on. And if you do that, then you get that, notice it's log base 10, by the way, not log base E. So we've switched from log base E normally to log base 10 here, and that's easy to miss because we normally talk about natural logs, base E, and don't forget that this is log base 10. All right, so I've switched log bases, I've put in all the numbers, I've chosen appropriate units, and I've pulled out all the stuff that actually matters, all the stuff that changes from solution to solution. So the ionic strength, the dielectric constant for water, and the absolute temperature in degrees Kelvin. And notice that given the units I've chosen here, ionic strength should be in molar units, and temperature should be in degrees Kelvin. Dielectric constant is unitless, so that doesn't matter. And this is the general formula, again, for all cases, even if you're not in water, even if you're not at 298 K. But if you are in water, and if you are at 298 K, which is the most common case, then all this boils down to something simpler. And actually, this formula has to have a Z plus, Z minus in it here. I'm sorry, I must have left that out. So I'll put that in the notes. I'll correct that in the notes when I actually post this version. But anyway, for the moment, let me just note that. Anyway, plugging in 298 and the dielectric constant for water, you get this even nicer formula. It's now 0.509, so no powers or anything. It's just about a half units of molar to the minus 1/2, which cancel these units of molar to the 1/2 that you're going to get from ionic strength, the charges on the ions. And if you invert that so that you can get the activity coefficient itself rather than the log, you get this nice formula which isn't at all hard to use. Here is a bunch of cases for a 1-to-1 salt. And we saw above that for 1-to-1 salts, ionic strength is just molar concentration. And so this is the sort of simplest case where the ionic strength effect is the least. Once you start going to +2, plus or minus 2 ions, or plus or minus 3 ions, the ionic strength effects get much, much bigger. We'll see some examples of that below. But in this simplest of cases, it'd be good to see how big or how strong an effect do these activity coefficients have. And so for 1 molar concentration, that's the ionic strength, the activity coefficient is 0.3. Remember, that gets multiplied by all the effective concentrations in the problem, and so that means that the effective concentration of, say, sodium chloride, if you're at 1 molar sodium chloride, or in the neighborhood of 1 molar sodium chloride, is only about a third what it would be if you didn't have ion-ion interactions. And even at 10th molar, it's still about 0.7, much down from the nominal concentration. At 100th molar, it's still significant, about 0.9. And even at 1 millimolar, it's still a significant effect. The effective concentration is only about 96% of the true concentration. So these activity coefficients have a big effect. They cause the effective concentration to be much lower than the true concentration, which means that things get more soluble, right? If you're dissolving sodium chloride and the solution behaves as if its concentration were actually lower than it truly is, then you're going to be able to dissolve more stuff. And we'll see that when we come to examples below. So I say again here that all of these things, all of these effects are much bigger if you have more highly charged ions, and again, we'll see that below. All right, so that's the Debye-Hückel theory straight. This is kind of the most useful formula right here, or all these formulas right here are the most useful ones. But I have emphasized that the Debye-Hückel theory has a lot of approximations in it. It's really only good in this last case down here, where we're in the millimolar range. A few millimolar in Debye-Hückel is still pretty good. But these activity coefficients are seriously wrong, or start being seriously wrong, especially for these higher concentrations. We'd like to fix that. We'd like to be able to deal with somewhat higher concentrations. We don't want to be stuck with just millimolar concentrations. And so there are a bunch of better approximations, and I give some reasons here for why those approximations have the effects that they do, but your book goes through these much better than I do. Engel and Reed goes through this much better. Here it is, section 10.4. Read that carefully so you understand what's going on, but I won't go through them here. All right, here are the better approximations. There's 2 of them I'm giving. Engel and Reed just gives one. They give the Davis equation here, the Davies equation here. I'm giving another one that I've seen elsewhere, and I actually think is more useful. It's called extended Debye-Hückel theory. And you can see that this top term here, that's just Debye-Hückel, but it adds a denominator which tends to make this left-hand side of the equation smaller when the ionic strength is a little bit bigger. You have to know the values of A and B here. Here they are for water at 298 K. I've never actually seen them for anything other than water at 298 K, though I'm sure they exist out there. Probably can find them if you Google. And the net effect is that this is more accurate. It's not a theoretically derived equation or relationship. It's just a fitting function, really. It's based loosely on Debye-Hückel, as you can see, but there really isn't any justification for this denominator. It's just that it works, and that's fine for our purposes. There is one parameter that you need to know. That's this effective ionic radius in angstrom units. Notice the units on B here, which appears there, are molar to the -1/2 to cancel the molar to the 1/2 units for that factor, and then angstroms to the -1 to cancel the units on A. So A is in angstrom units. And for some typical ions, it's about 3 angstroms. It can be a lot larger. It can also be smaller. You have to know that number for the type of solution that you're working with. But this expression will work in general for much higher concentrations than Debye-Hückel does. The Davies equation is kind of similar. It's also got you notice this part of the equation right here is Debye-Hückel again. And when I is really small, this will all reduce to Debye-Hückel. So all these, Debye-Hückel is right, is correct, is rigorously correct for small enough concentrations. So all these things reduce to Debye-Hückel at small concentrations. But it's also got these correction terms, which again account for some of the approximations that are present in Debye-Hückel. Again, this is all good for water at 298 K, and in this case, again, ionic strength in molar units. All right, so let's look at a comparison between Debye-Hückel, extended Debye-Hückel, and the Davies equation here, just to see how much difference there is between the three. And here I say these are the measured numbers, the actual experimental numbers. I took these from figure 10.6 in your book. I couldn't find them anywhere better. And so these are not really accurate, but they're good enough for our purposes at the moment. So starting from low concentration and going all the way to 3 molar, which is pretty high, the concentrations do get higher than that. Seawater, for example, is about 4 molar, so even higher, but still pretty high concentration. You can see Debye-Hückel gets very small by the time you've gotten to 3 molar concentration, but that's quite wrong. The real ones aren't that small. So here's the extended Hückel prediction, here's the Davies prediction. Notice the Davies prediction says that the activity coefficient actually gets bigger than 1. The Davies equation is saying that if you go to really high salt concentrations, the salt behaves as if the effective concentration was actually bigger than the true concentration. It's acting as if the ions were anti-pairing, were repelling each other, and that's actually what happens. In fact, that's one of the things that Debye-Hückel gets wrong. There are strong repulsion effects when the ions get big enough due to a whole bunch of things. Again, Engel and Reed talk about that. So this fact that gamma actually gets bigger than 1 for very high concentrations is a true experimentally observed fact. Davies gets it, extended Debye-Hückel doesn't. So at very high concentrations, I suspect Davies is the best case. But at intermediate concentrations, right in here, for example, between 100th molar and 1 molar, I think extended Debye-Hückel is actually better. Anyway, here's the comparison. You can see at 100th molar, they're all pretty much the same. At 10th molar, extended Debye-Hückel is a little bit bigger than the prediction of Debye-Hückel. Debye-Hückel's starting to overcompensate for ion-ion attractions, and in pretty close agreement with the actual measurement. At 1 molar, somewhere in between these two is what I got from the graph. I'm not sure that that's a good number, though, so don't take it too strongly. Anyway, both of these are okay, and this is maybe a little high. The Davies equation probably isn't, well, it seems to me right now, isn't working quite as well as either of these two in this sort of intermediate 1 molar range. All right, the extended Debye-Hückel again looks the best for the intermediate range. All right, so that's the Debye-Hückel and related versions of the activity coefficient. Let's do some actual examples. Let's see how this works. I've got 3 examples here, and I'm going to do just 2 of them, one being looking at the actual solubility for calcium carbonate, and the other one is one of your homework problems, example 10.7 from Engel and Reed, so we'll look at that one also. Let's look at this solubility problem first. So in this case, the chemical reaction. So what we're going to try to do is solve for the actual equilibrium concentration of ions in solution, that is the solubility. You put a bunch of solid calcium carbonate in solution, you let it sit there for however long it takes, you let it come into equilibrium with some solid, and you reach the solubility limit. That's what we're calculating. So first of all, we need to get the equilibrium constant for that chemical reaction. Here are the delta G numbers from the tables in the back of the book. Now, this doesn't give a real accurate equilibrium constant, but I did it this way because it's good to see that you can use these numbers in the back of the book to actually get equilibrium constants if you don't have the equilibrium constant from some other source. The measured equilibrium, this is a little bit off. The measured equilibrium constants, the real value is about 3.4 here, not 4.9. The measured equilibrium constants are more accurate, but you can get a decent approximation or estimate of equilibrium constants from the tables in the book, and that's what I did here. So, these are the values from the book. I calculate the delta G of reaction here, and it turns out to be kind of modest, about 50 kilojoules per mole. I put that into the formula for the standard formula for, this is a delta G0, of course, a standard state delta G, all as if these were 1 molar, even though they're not going to even get close to 1 molar. I put that in to get the equilibrium constant, and I get something 10 to the 9th. It's that 9 that matters the most, that order of magnitude. This value out here matters to a small extent. Like I say, it's wrong for this value right now. It's closer to that, but anyway, good enough for our purposes. That means that the Q for this factor, assuming that the solid is pure, is gamma times the concentration of calcium, gamma times the concentration of carbonate ions. Let's call both of those concentrations equal to X. They both have to be equal, right? There wasn't anything in the solution to start with. Every time we create a calcium ion, we got to also create a carbonate ion. That means we're going to have as much calcium as we do carbonate in solution. That means the concentrations of both are going to be the same, so we'll call them both X. That's the variable we're going to try to solve for. If we plug that in here and here, we get that at equilibrium, the equilibrium constant has to be equal to this activity coefficient squared, because we've got 2 activity coefficients here, times X squared. That means that if we solve for X, we get the square root of the equilibrium constant divided by the activity itself. And we could plug numbers into that if the activity weren't itself a function of concentration, but it is, so we're going to have to do something a little bit more complicated. So here's the problem, right? The activity coefficient is a function of the ionic strength, and the ionic strength depends on the concentrations of the species themselves. So this isn't a closed equation. We're not solving for X here. We've got something that depends on X over on the other side. So, defining the ionic strength in this case, we have that the charge on the calcium is +2, the charge on the carbonate is -2. This quantity Z plus Z minus is therefore 4. That goes up in here. And then the ionic strength isn't concentration, remember, it's just kind of related to concentration. It's 1/2 charge on calcium, concentration of calcium, charge on carbonate, concentration of carbonate, and that works out to be 4 times the value of X, which is the carbonate or the calcium concentration. So what are we going to do to solve this? We've now got dependence on X on both sides of our equation here. We're going to do it iteratively, which means that we're going to start out by choosing the activity coefficient to be 1, because we don't know any better. We're going to use that to find a value for X. It's the wrong value, but it's a first guess. Then we'll use that X to recalculate the value of the activity coefficient. We'll use that to calculate a new and better value of X, and we'll just repeat that process over and over again until everything converges and one recalculation doesn't change the answer from the previous recalculation. So repeat until we get convergence or X no longer changes. Here's an example of that in practice. So I start out on cycle number 1 here, assuming that gamma is 1. I use that gamma of 1 with this formula here to calculate X. So I'm calculating X with gamma equal to 1 here. And I get then 7.05 times 10 to the minus 5. Notice that X turns out to be a very small number. That's what you'd expect. Calcium carbonate is not very soluble. Generally speaking, all these methods work best when the number you're calculating is going to be a small number. And I won't go through all the stuff people normally say in freshman chemistry. You've done these kinds of problems before. So I'm hoping you remember enough of that so that all this will be familiar to everybody. All right, now I have a new value for x. I plug that into the formula above, right? This formula. So I'm plugging 4x into there. I'm plugging that into there. I'm plugging this 4 into there. And that's what this formula is here. There's the 4. There's the 4x. And that gives me a new activity coefficient, which isn't 1 anymore. It's a little bit smaller than 1. I use that to calculate a new x, right? I'm using this formula again here. There's my calculated activity coefficient. There's my square root of k. And I get a new concentration, which you notice is a bit bigger, right? Because the activity coefficient was smaller. The ions aren't acting like their full concentration, so they, a little bit more of them can dissolve. And so you get 7.62 times 10 to the minus 5. Now we repeat all that, plug in, get a new activity coefficient, 0.921. That gives 7.65. I repeat that again, and I get 7.65. Again, now I've converged, and that's my final answer. So, to summarize, if I hadn't used the activity coefficient, I would have predicted this answer, right? This is the answer without activity coefficients, and that's 70.5 micromolar, sorry. 70 micromolar. On the other hand, when I do the full calculation, I get something like 76.5 micromolar. So there's about a 9% difference between these two answers. That's something you could neglect in some situations and couldn't neglect, would cause big problems in other situations. So depending on your situation, this extra work that we had to go to calculate this better number might be worth it and might not. Depends on the situation. All right. So that's the first case. That's solubility of calcium carbonate. Let's look at the problem from your homework, pH 10.7 from Engel, problem 10.7 from Engel and Reed. Now we're looking at the dissociation of an acid. So we've got some acetic acid in solution. It dissociates to acetate ion and H plus ions. We have the equilibrium constant now already. I didn't calculate it from delta G values like before. 1.75 times 10 to the minus 5. In this case, the Q for this reaction is activity for acetate, activity for hydrogen over activity for acetic acid. And now this activity for the first time, this activity for acetic acid is not an ion, it's an actual concentration. So this boils down to, after plugging in the activity coefficients, gamma plus minus for the acetate, gamma plus minus for the hydrogen. The acetic acid molecules aren't ionic species, so we make the approximation that the activity coefficient for that species is just 1, and we ignore it in the rest of the calculation. Now we're doing a freshman chemistry calculation, a pH calculation, just like you did probably ad nauseum in freshman chemistry. And I set up an ICE table or ICE table here to get everything straight. I won't go through that. You can look at that in the notes at your leisure, but that gives this equation that we now have to solve. X is the concentration of either acetate or hydrogen ion. That's what we're trying to solve for. Normally, we'd have to solve a quadratic equation here. Now we have to solve something even harder, and that means the quadratic equation won't work. And that means we should do the solving iteratively again. And again, that works if this x isn't too big, especially if this x is not too big compared to the initial concentration. So this is the initial concentration of the acetate ion, the acetic acid itself. And if this dissociated concentration is much smaller than the initial concentration, then the iterative solution will work pretty well. And so let's consider that case. Let's consider the case where the initial concentration is 0.15 molar. Kind of small, but a decent concentration, not a really tiny one. And let me point out, actually I should have pointed out this before, your book uses mole-al units throughout this whole section. I don't know why. I've never seen that before. I'm going to use molar. That agrees with practically everybody else in the world and is also theoretically better justified and also more convenient. So I don't know why the book likes molal, but anyway, I'm not going to use molal. The formulas don't change because, in fact, they're very close to each other. Okay, so solving for x using this formula above, I get that x is equal to all this stuff, but notice that x is on the other side here. It's also buried inside this activity coefficient. So I'm going to use the same iterative scheme we used last time. I'm going to assume x is 0 here to begin with. And I'm going to assume that this is 1 on the first cycle. I'm going to use that to calculate x, get a better x estimate, and just keep cycling after that. So here we go. We set gamma equal to 1. I set that equal to 0. I use that to calculate the new x. I get 1.62 times 10 to the minus 3 there. There's another mistake that I have to correct in the notes. Use that to plug in both to get a better value for C0 minus x. You can see C0 minus x is still very close to what it was. And to get a new value for gamma, which is now a little bit less than 1. Use those to plug back in and get a better value for x and continue cycling. And after just 3 iterations, I've already converged, and the answer is about 1.69 millimolar for the final corrected activity coefficient corrected concentrations of DH plus and the acetate ion concentration. Now, the problem asks you to compare what you would have gotten if there were no activity coefficients, if you didn't account for ion-ion interactions. And so to do that, I solved the quadratic equation just like you would in freshman chemistry. Here's the quadratic formula. Here's the answer you got. You get 1.61 times 10 to the minus 3 molar, or 1.61 millimolar. So summarizing again, without the corrections, you get an H plus concentration of 1.61 times 10 to the minus 3 molar, and you can use that to calculate a pH using the normal formulas, and it turns out to be about 2.79. If you do the corrections, you get 1.69 as the concentrations at 0.15 molar, depends on what this initial concentration was, and that gives you a pH of about 2.77. So there isn't very much difference between these two. There's a somewhat more significant difference between the actual concentrations, a few percent difference, and again, depending on the application, that would either be significant or not. The problem also asks you to repeat this whole calculation for 1.5 molar, so now you've got a much higher initial concentration, and I won't go through all this, but there it all is again. It takes now quite a little bit more work to get it to converge, and again, you can compare to the uncorrected case, and you get about a pH of 2.29, a little bit yes, a little bit, oh, sorry, no. So that is, yeah, I don't know, that's right. So what is it, yeah, okay, yeah, a little bit lower pH, right. And a little bit difference in pH between the two cases, but again, not a very big one. All right, finally, this third case I won't go through. This is the concentration of calcium sulfate, which is a lot more soluble than calcium carbonate. You can see the equilibrium constant here. I calculated, here it is, where is it? There it is. It's 10 to the minus 5 now. For calcium carbonate, it's 10 to the minus 9. So this is a good deal more soluble. And in this case, what's interesting, and I think you should go through this case carefully, because this is a case where the concentrations get high enough so that the Debye-Hückel approximation isn't good enough. I use the extended Debye-Hückel law here in order to get something that actually is reasonable with the Debye-Hückel approximation itself. You get quite unreasonable results. So go through this in detail. It's a little bit more complicated than the other cases, and let me just show you it took quite a while for the problem to converge, 8 cycles before it finally converged. And in this case, without the correction, we calculated a calcium sulfate solubility of only about 8 millimolar, but with the correction, the calcium solubility is 25 millimolar, so almost 3 times the size of what you would have predicted, and that's because the ion interactions are now really serious. And so what this problem illustrates is that these ion-ion interaction effects and activity coefficient effects can have a really big influence in some cases. Again, let me urge everybody to go through this case. It's not assigned as a homework problem or anything, and we didn't go through it in detail, but please go through that case carefully to see how things work both when the ionic strength isn't so small, isn't in the millimolar range, and also when you have to use one of these better approximations, extended Debye-Hückel or Davies approximation, in order to do this iterative calculation. And that is it. We'll stop there and go on to Chapter 11 next time.